Example 6, find inverse of exponential functions. So the Richter scale measures earthquake intensity. The increase in intensity between each number is 10 times as strong. So if you have a earthquake of 3.0, an earthquake of 4.0 is 10 times as strong as that last one. Um, and they actually say that in the example here. For example, an earthquake with a rating of 7 is 10 times more intense than one measuring a 6. The intensity of an earthquake can be modeled by the function y equals 10 to the x minus 1, where x is the Richter scale rating. And there's a little bit of real world information here that we're going to use, so I'll read that out because it might be kind of small on your screen. The largest recorded earthquake in the United States was a magnitude of 9.2. So 9.2 on Richter. Richter scale. And it happened in the Prince William Sound, Alaska, on Good Friday, March 28th, 1964. This was such a big earthquake that up in Trinidad, up by Humboldt State, the there was a lighthouse that they had on top of this big rock on the outside of the harbor in the town. It was so big it knocked. There was a tsunami that came from it. It like destroyed a huge part of the town and actually moved the lighthouse to a different spot. And if you were to go to Trinidad now, they actually left it where it was so you can see how far it moved from where it was. It's straight up like it moved it like a quarter mile. It was crazy. It moved it super far. So huge tsunami came with this as well. It destroyed a few towns on the west coast. All right. So um, use the information about the Good Friday earthquake to find the intensity of the strongest earthquake in the United States. So the idea here is X is the Richter scale. So I can plug in here y equals 10 to the 9.2 minus 1, and I can figure out the intensity. And so that's just y equals 10 to the 8.2. Plug that into my calculator. 10 to the 8.2, and that is y equals 158489319.2. That is a gigantically large amount of energy, right? Think about that here. Comma, 158 million times as strong as a Richter earthquake of 1, which are happening all the time. So huge, huge difference in the amount of energy in it. Let me make sure that the book and I agree on this number here. We should. Yeah. All right. So for part B, what we're going to do is we're going to write an equation in the form of a logarithm with base 10 for the inverse of this function. So the idea is I'm going to take y equals, oh sorry, it wasn't supposed to be plus 1, it was supposed to be plus c. I was wondering why the plus 1 was there. It's supposed to be plus c. So we're looking for a constant. So y equals 10 to the x minus 1. So my base value is 10, log base 10. My input is the oh shoot, that's why I'm getting all confused here. Let's go ahead and swap these things here. X equals 10 to the y minus 1. I'm finding the inverse, so I have to switch the x and the y. Now let's find the logarithm. Log base 10. The input is the result x, and it equals the exponent. So go ahead and add 1 to both sides. So log base 10 of x plus 1 equals y. That's why I wrote it down. I just solved the problem before, and it confused me in all of this stuff here. So the idea with this is you plug in the energy, like this big nasty number up here, get the Richter scale. So that's how scientists are going to find the Richter scale. Like there's a uh, earthquake in Willits the other day. They, based on how much their machines were shaking, it was able to calculate how much energy it was. They plug it into this formula. The output is the Richter scale, and so then they can report, oh, we had a 4.1 earthquake in Willits. Um, the machines do other things too. The seismographs, they also tell you location, but you have to have 3 of them to do that. You triangulate it. Um, but yeah, that's all you do. Sorry that one confused me because I had the answer in the question. But if we're finding the inverse, switch the x and y, change it from exponential form to logarithmic form, and you'll get it.